Welcome back to another explainer. Today, we're diving straight into the spatial domain to see exactly how median filtering works to save ruined images. If you've ever dealt with digital photographs that just look totally corrupted, spotty, or degraded by random pixels, you are going to find the mathematical rescue mission we're covering today incredibly satisfying. Here's our roadmap for today's explainer. We'll start with 1, fixing salt and pepper noise. Then 2, prepping images with padding. 3, the 3x3 filter mask. 4, arranging and selecting the median. And finally, 5, scanning the entire image. Starting off with section 1, fixing salt and pepper noise. So imagine your absolute favorite photograph is suddenly covered in these tiny, harsh black and white dots, just scattered completely at random. How do we pull off the mathematical puzzle of cleaning them up? And here's the real kicker. How do we do it without turning the entire picture into a blurry, out-of-focus mess? Well, the technical term for those annoying spots is actually salt and pepper noise. Pretty fitting, right? It literally looks like someone took shakers of stark white salt and pure black pepper and just sneezed them all over your digital canvas. Now, you might think, hey, let's just smooth it out with a standard averaging filter. But our sources point out that is a terrible idea here. If you take a pure black dot and average it with the normal pixels around it, you don't delete the dot, you just smear it into this ugly dark gray smudge. It blurs the noise right into the background. To actually eliminate that harsh salt and pepper noise, we have to ditch the simple linear world of averaging. Instead, we're stepping into the nonlinear realm of median filtering. A median filter doesn't want to blend the noise into the image. It wants to completely reject it and swap it out for something accurate. It's an absolute game changer. Which brings us to section 2, prepping images with padding. Before we can unleash our median filter, we have a tiny logistical problem to solve with the image boundaries. Think about it. A filter needs to look at a pixel and all its immediate surrounding neighbors. But what happens when your filter hits the absolute top left corner of an image? Boom, you run out of data. Half your filter is just hanging off the edge into nothingness. Since those edge pixels need a full neighborhood to be calculated properly, we literally have to build an artificial boundary around the picture first. Our sources highlight 2 main ways to solve this boundary problem. The first is called pixel replication. That's where you just take the existing outer rows and columns and push them outward, basically copy-pasting the edges to make a buffer. The second option is zero padding, and it's exactly what it sounds like, wrapping the entire image in a protective border made of pure zeros. It's kind of like digital bubble wrap. Once the image is padded, our filter can safely process every single real pixel without falling off the edge. Moving right along to section 3, the 3x3 filter mask. Now, with our image padded and prepped, here is our primary tool for the operation. I want you to visualize this empty 3x3 mask as a tiny digital magnifying glass. We're going to drop it directly over our image. It covers exactly 9 pixels at a time, the 1 target pixel sitting dead center, and the 8 immediate neighbors surrounding it. All right, section 4, arranging and selecting the median. Let's actually slow down a bit here, because this is where the nonlinear magic really happens. Step 1, we place our 3x3 mask down and extract the intensity numbers of all 9 pixels. Step 2, we sort those 9 numbers into a strict line. Highest to lowest or lowest to highest, it doesn't matter. Step 3, we count exactly to the 5th number in that line to find the exact middle, the median. And step 4, we take that median value and overwrite whatever noisy junk was in the center of our mask. Let's see this in action with an actual example. Check out this microscopic view of a 3x3 block. The surrounding pixels are pretty normal, healthy values, right? 125, 128, 130. But look at the center. It's corrupted by a nasty speck of pepper noise sitting at 33. It's aggressively dark compared to its neighbors. If we average this block, that 33 would completely drag the math down and leave a dark shadow. We are definitely not going to do that. Instead, we take all 9 numbers from that block and forcefully line them up. We're using descending order here, highest to lowest. Notice how we completely ignore their original 2D position in the grid? Think about the genius of this. If there's extreme white salt noise, it gets shoved all the way to one end of the line. And extreme black pepper noise, like our 33, gets shoved all the way to the other end. So, looking at our freshly sorted list of 9 numbers, we simply count into the 5th spot.
Since all the extreme noise values got banished to the far edges of our line, the exact middle value is guaranteed to be a healthy, normal pixel from that neighborhood. And for our example, that median value is 125. This is the most satisfying part. We immediately chuck that noisy 33 in the trash, it's gone, and we replace it with our newly discovered median of 125. Just like that, we've successfully cleaned that tiny microscopic block. The center pixel now perfectly matches the visual context of its neighbors, and we didn't blur a single detail to do it.
Finally, Section 5, scanning the entire image.
We saved one pixel, but we've got a whole photograph to clean. So we have to get the mask moving. The process is super systematic. Once that first pixel is updated, the 3x3 mask slides right by exactly one column. It captures a new set of 9 pixels, sorts them, grabs the median, and updates the new center. It just ticks across the image one column at a time until the row is completely swept. Then it drops down a level to the next row, shifts all the way back to the left, and starts the rhythm all over again. Our sources actually phrase it perfectly. You are circulating this mask over the complete image to update every pixel. That continuous rhythmic sweeping is what does the heavy lifting. By forcing every single pixel through that strict sorting and median selection process, it systematically wipes out the salt and pepper noise across the whole canvas, leaving behind a crisp, clean photograph. Now, we achieved all of this today using a compact 3x3 digital magnifying glass. But I want to leave you with a provocative thought as we wrap up. What if we expanded the size of our mask? Say we used a 5x5 mask, grabbing 25 pixels at a time, or a 7x7, pulling 49 pixels. Would it clean up larger clumps of noise? Or would it start to accidentally erase genuine fine details in the photograph, like the texture of a leaf or the sparkle in an eye? It's a fascinating trade-off in the spatial domain to think about. Thanks for hanging out with me for this explainer, and keep exploring.